So in Calc 1, you investigated two primary problems in the subject of calculus. The first one was, you know how much of a quantity you have at every moment, and you want to know how fast that quantity is changing at every moment. And then the second primary problem of calculus is the flip side of that. You know how fast a quantity is changing at every moment, and you want to know how much of it you have at every moment. Okay, so these are the two main problems that kind of encompass all of calculus. So that's what you did. Now, some of you may not know that that's what you were doing, but that's what you were doing, okay, or should have been doing, okay, in Calculus 1. So Calc 2 explores both of these, but most of the course is concerned with endeavor number 2. Most of Calc 2 is about, you know how fast the quantity is changing at every moment, and you want to know how much of it you have at every moment. So what we're going to do in this first week is we're going to do a crash course in Calculus 1 of problem number 2. That's what we're going to do this week. So we're hopefully in 3 days, we're going to get through what we spent about a month on, or even 5 weeks in Calculus 1, which was number 2. You know how fast the quantity is changing every moment. You want to know how much of it you have at every moment. Okay, so to review this, our crash course, I've made a set of principles. I made a set of principles that kind of walk us through this problem and build it from the ground up. So principle number 0, so before we even kind of get to it, I have a principle 0, and that's this idea that variables vary. Variables vary. Super important idea. All right, so when you see this, 2x minus 7 equals 0, what do you think? What comes to mind? What's that? X equals 7 over 2. Is that what you're saying? 7 halves, right? So x has a value, and you solve for x, and you get it, 3.5, right? So could x be 4 or 10 or negative 0.5? Yes or no? Could x be another value? Anyone say yes? What would happen if x was 4? You get 1, right? So really, if x was 4, then we could just say that thing wouldn't be true. So like we could say x could be 4, but then that equation would not be true, right? Okay, so that's actually a better way to think about this. Rather than thinking x is this value and it's not changeable. So no, x could be other values. But of all the values x could be, there's only one that makes that equation true. That's a stronger way to think about this. Okay? So suppose x was defined as the number of hours elapsed since your plane left the ground. Okay? So there's the same x as above. Now it's the number of hours gone by since your plane left the ground. Now could x be 4? Does that feel comfortable to you? And what would that mean? Yeah, you've been in at that moment. You've been in the plane for 4 hours, or the plane's left the ground 4 hours ago, or 10 hours ago. What about negative 0.5? Does that make sense? Was it? Someone said? Yeah, half an hour. So it's possible. So negative 0.5 could just be a half an hour before the plane took off, right? Half an hour before the plane left the ground. Okay, so we want to think about variables as taking on lots of values. And some real-world situation is occurring, and x is changing as time goes by, or as this situation is unfolding, x is taking on values. So x is 0, so the plane's taking off. X is 0.2. We're a fifth of an hour in. X is 1. We're 1 hour in. So as we're experiencing this plane ride, x is constantly changing. X is constantly varying. All right? That's how we want to think about variables. All right, so what about dx is a symbol you saw in Calc 1. That's actually a variable too. What does dx represent? What does dx represent? Okay, so it's some amount of change in the value of x. Okay, so in this case, dx would be a change in the number of hours elapsed. All right, so what's the difference between saying The difference between x equals 3.5 and dx equals 3.5. So x equals 3.5. X means the amount of time elapsed since the plane took off. So that is a moment in time. That is a moment in time, 3.5 hours since the plane took off. But what about dx equals 3.5? Is that the speed? No, it's a change in x. So what does that mean, a change in x? Starting from when? Yeah, so it could start from any x value. So this dx of 3.5 could start from, say, 1. All right, and then when would that dx be up? At 4.5, right? And so that dx then represents this amount of change in time starting from 1 and ending at 4.5. But that dx could also start at 5 hours, and then it would be from 5 to 8.5. Dx would represent a change from x from 5 to x equals 8.5. So dx is a different animal, right? It has the same unit. It's still hours, but it represents a change starting from some or any value of x and then lasting, in this case, 3.5 hours to some final value of x. Okay? So, important concept. Dx is then a change, an amount of change in whatever our x variable is, in this case, the amount of change in time since the plane left the ground. Okay, so, now I hope this, hopefully this works now. Yes, good, okay. Principle 1. Okay, so principle 1, so you know how fast the quantity is changing at every moment, and you want to know how much of it you have at every moment. So that problem, what does rate of change have to do with that statement, that problem? You know how fast the quantity is changing every moment. You want to know how much of it you have at every moment. So rate of change is what in this statement? Yeah, how fast a quantity is changing at every moment. How fast a certain quantity is changing, that's the idea of rate of change. That's the idea of rate of change. So this is a key kind of underlying principle because it's what you would start with in this problem. It's what you would have. You would know how fast the quantity is changing every moment. Or in other words, you would know the rate of change profile for this quantity. So we're got to know about rate of change. All right, so let's do a little easy example here. So you're buying trail mix that costs $3.20 per pound. After scooping some mix into your bag, you decide you want more. Because that's what we're like in America. We want more, right? And what additional cost will you pay for 1.5 more pounds of trail mix? Everybody figure it out. So any way you can, get the answer to this question on your own, okay? On your own. How much will you pay for 1.5 more pounds of trail mix? So how much more will you pay when you put 1.5 more pounds in your bag? So who got a quick calculation to do that? Yes, sir? And how'd you get that? 3.2. You took 3.2 times 1.5. And you got? $4.80 is how much more you would pay for 1.5 more pounds of trail mix. Everyone agree with that? All right, let's hold on to that thought for a second. So in calculus and most of mathematics, what's a really important skill is you're taking a situation, a real-world situation, and we're modeling it with mathematics. What does it mean to model it with mathematics? What that means is we're going to assign symbols to model the situation, represent the situation. So here's a set of symbols that I have. These are variables, right? So x, y, dx, dy, and m. So what I want you to do quickly is I want you to write phrases that represent what all these 5 symbols mean in this situation. So let's do x together. What do you suppose, if we're looking at a kind of conventional way of assigning? All right, so he said the number of pounds. Agree with that? We'd be a little more specific than that. So yeah, that's right. Yeah. Okay, yeah. So I just threw in total in there. The total in your bag, right? So it's like the total amount of trail mix in your bag is X. So I want you to and you can collaborate with the person next to you. See if you can, in about 1 minute, finish these other four. You're writing out phrases that represent these symbols. Go. Oh, and then the other thing is, in addition to the phrase, then you're gonna determine, do you know the current value of these for this situation or not? So given X, given Y, for each one of those, ask the question, do you know its current value with the situation that I've given you? Okay? Commence. Okay. So, see if this is what you came up with. Y would be the cost of X pounds. So the cost of the trail mix in your bag in dollars. DX is change in the number of pounds, right? Change in the number of pounds. DY then is the change in cost. And I'm using M to mean what? That's kind of a conventional use. Yeah, that's the price per pound, that's our rate of change. In this case, it's a constant rate of change, right? It doesn't matter how many pounds are in your bag. It's always $3.20 per pound. Okay, is X known in this situation? Given the setup for this scenario, is X known or unknown? Unknown. We don't know the total number of pounds, right? I just said you put some in and then you put some more in. We don't know that initial amount, so we don't know what X is at. What about Y? Nope. Do we know DX? What is DX? 1.5, right? So this is the idea. If you have a certain amount in there, you put this much more in, that's the idea of a change in X, right? DX would be the 1.5. All right, DY? That was that number we calculated, right? 480. And of course, we know M, right? X and Y currently unknown. Okay, so I'm going to write an expression. Sorry, I wrote in a bad place there. So write an expression using two or more of these symbols that represents this problem up here. So we had a little calculation that we did. So I want to apply these letters now, these variables, to that, and come up with an expression or an equation that represents that using either x, y, dx, dy, and or m. So what would it be? First of all, what did it solve for? What were we asked to find of these five? What were we asked to find of these five? dy. It was asking for how much more it would cost. That's our dy. And how did we find dy? He wants m dx. Agree? Yep, m dx. And so we could say for this particular scenario, we could be a little more specific and say that dy equals what? 3.2 dx. So what does $3.2 per pound mean? What does $3.2 per pound mean? What's the meaning of that value? For every pound that you have, you're going to pay $3.2. Agree with that? Okay, that's absolutely true statement, but that's a very narrow meaning of the 3.2. Okay, so this next part is maybe the most important part of today's lecture. Okay, that is absolutely true, that every pound that you have costs $3.20 pounds. $3.20. Okay, every pound that you have will cost you $3.20. But a much broader meaning would be that really, what? This little equation here, dy equals 3.2 dx, gives us a much broader meaning of that 3.2. Does it tell us anything more than how much 1 pound is? Does it tell us how much 2 pound is? How much is 2 pounds? 640. Does it tell us how much a half a pound is? $1.60, right? Does it tell us how much 10 pounds would cost? Really, it tells us. Here's the key. This is today's most important thing. Given any change in pounds, the $3.20 tells you how much the change in cost would be. That's what that equation says, and that equation is how it explains that $3.20 per pound. Right? dx could be anything. It's a variable. It could be a half a pound. It could be 2 pounds. It could be 8 pounds. It could be 20 pounds. And given a change in the number of pounds, 3.2 will always tell us what the change in the cost will be. Do you see how that's much more broad and inclusive than just 1 pound costs $3.20? We know how much any change in pounds, what change in cost we'll get. All right? So in that equation, so this equation is how we frame the meaning of that constant rate of change, $3.20. Okay? So again, one more time. Given any change in the number of pounds, the change in the cost will be $3.20 times that change in number of pounds. That's the meaning of a constant rate of change. Okay? Make sure you review that in the video. Get it in your notes. Most important thing of the day. Okay, going on. We remove 0.4 pounds from the bag and return it to the bin when no one's looking, right? When no one's looking. What is dx now? So it has the same meaning. What's its value? Negative 0.4. How would we find dy? Right, dy is always m dx, or 3.2 in this case, dx. And we said that we know what your change in cost will be for any change in number of pounds. So it'll be 3.2 times negative 0.4, which is, 8, what is it? $1.28? Is that right? Really? You get it? Yeah, I think so. Okay. So what does that mean? That means if you put that much back in the bin, your cost is going to go down that much, right? Your change in cost is negative, meaning your cost will go down. M is still the same than 3.2. So that's an example of, here's something else that 3.2 dollars per pound tells us. It tells us that if we decrease the number of pounds by negative 0.4, our cost will go down $1.28. Questions on that? All right, new example. Soldier lowers an American flag from the top of the pole at 0.75 meters per second. So here's the question we want to explore here. How much does the height change from 0.6 seconds to 2.4 seconds since the flag left the top of the pole? So if you were given this situation, what should you do first? What should you do first? Model the situation with letters, with variables, parameters, okay? So again, let's define what x is, what y is, dx, dy, and m, and I'm giving you y here. I'm going to say that y is defined as the height of the flag in meters. So y is I want the height of the flag above the ground, okay? So you do the others. So write phrases for x, dx, dy, and m. And then determine if they're known or not in this situation, right? Same thing as before. So write the phrases, and for each one, determine if it's known or not in this scenario. Take 2 minutes max. 2 minutes. Go. You can collaborate, but you definitely at least want to check when you're done. Okay. What is x? The rate? The rate of time. So is it a rate? Is x a rate? Okay, so it's definitely a time variable, but time, if you said time in seconds, that's definitely not specific enough. We could define 10 or more different time variables that are all different in the situation. So we know exactly what amount of time we're talking about. And so that means a reference point, right? So time since he started lowering the flag. All right, so time since the soldier started lowering the flag. You need that reference point of what is time 0. If you don't have that reference point of time 0, it's really not clear exactly what time quantity you're talking about. Okay, Y we already said, height of the flag. So dx would be then any change in number of seconds, right? And we said that could start from any time x, right? It could start from any time x, and it represents a change in time, an interval of time. You can think of it that way, a duration of time. All right, dy is a change in the height of the flag in meters. Okay, and what is m? Again, we have a constant rate of change here. It's the constant rate of change. And what is the constant rate of change? 0.75 meters per second? Okay, so height defines that positive is which way? Up. Positive, or height increases going up. And if it's going down, then that rate of change is going to be negative. So if you picked up on that, good for you. That's important. That rate of change is negative because we have a decreasing height as time goes by. Do we know what x is in the situation? Do we know the value of x? Yeah, exactly. So yes, we do know. We do know that our starting x is 0.6, and our final x is 2.4. So really, x takes on all those values. In this situation, x is taking on all the values starting at 0.6 seconds up to 2.4 seconds. Variables vary, right? So yes, so it's taking on all the values starting at 0.6 to 2.4. Do we know the height of the flag? We don't know because we don't know what? The starting height. All right, so y is truly unknown. Okay, what is dx in this situation? Good, 1.8, right? So dx you could write as x final minus x initial, which are just two different values of x, our number of seconds. So it would be 2.4 minus 0.6, or 1.8 seconds. If you came up with 1.8, good job. That's the duration of time. So then what is dy? What did we say? So dy would be m dx, right? Remember, so this negative 0.75, does it tell us just that the flag goes down 0.75 meters every second? Is that what it tells us? That's a very narrow meaning, right? So it tells us what? In any change of seconds, how much the flag will go down, including 1.8. How much does the flag go down every 1.8 seconds? Well, we're going to take our negative 0.75 times 1.8, and you get, who did it? Nice and loud? 1.35 meters. Right? So given any change in time, that negative 0.75 meters per second, that constant rate of change, tells us the change in height for that change in time. Not just for 1 second. Any change in time, right? Including, in this case, 1.8 seconds. Gotta move. All right, so now we want to know, let's say, how much does the height change from 0.6 seconds to x seconds? So now we're going to let that final time be variable. And I want to know how much does the height change from 0.6 seconds to x seconds. So we're going to use dy equals m dx to do that. What is m? Negative 0.75. What is our dx now? Some of you are saying it. X minus 0.6. X is allowed to change now. So starting at 0.6 seconds, x is going to change. Now x is still the number of seconds since 0 seconds, since the flag left the top of the pole. It's not the number of seconds starting from 0.6. It's still the number of seconds starting from when the flag started to be lowered. All right, so we want the change in height. We got the constant rate. We got the change in the number of seconds. And so this question is equivalent to asking, really, what's the net accumulation function? Net accumulation function for the flag's height beginning at 0.6 seconds. In other words, how much height has accumulated since 0.6 seconds? Or deaccumulated, right? So it's decreasing, but accumulation can be increasing or decreasing. So this question is something called a net accumulation function. Okay? And so our dy, this is going to be our notation for a net accumulation function for a sum. This is the quantity h, or height. So it's the accumulation of quantity h, and that's our dy. How much has the height changed since 0.6 seconds? And we came up with that. You guys said that the m was negative 0.75, and dx would be x minus 0.6. So this is a net accumulation function of height, particularly for the net accumulation since 0.6 seconds after the flag started being lowered. Okay, and so this is what we call function notation. You're going to be practicing this stuff in recitation this week. Super important. What function notation means. It means the value of the dependent variable of this function. So there's an independent variable, and that's time since the flag started being lowered. That's x. And there's a dependent variable. And in this case, that dependent variable is the accumulation, the net accumulation of height since 0.6 seconds went by. All right, so that's principle number 2. So principle number 1 is just the idea of rate of change and what it means. We said that was the most important thing we covered today. Remember that? Principle number 2 then is a net accumulation function, like the one we just came up with. So same scenario. First we want to label, so I want to have a rate of change function on the left, and I want to have the net accumulation function on the right. So first of all, what would my units be? So we're going to do it as the rate of change function and the net accumulation function. What would my x-axis units be? So my horizontal axis units be on these graphs. That would be my x, right? So that would be my number of seconds since the flag started being lowered. What would be the units on the left graph of the vertical axis? It's the rate of change. Meters per second. That's the rate of change of height. And then for the net accumulation, meters. Okay? So what would the rate of change function look like if we were to look at, for any number of seconds, this graph is going to tell us what the rate of change is at that number of seconds. What would it look like? Horizontal line at negative 0.75. That's the rate of change function. Now, forgetting about the formula that we came up with, just based on the situation. So don't try to graph the formula, but think about what will this net accumulation function look like? At 0.6 seconds, what's the net accumulation of height since 0.6 seconds? 0. And then what happens to the accumulation of height? Goes down, right? So imagine it's going to start at 0.6 seconds, it's going to be 0, and it's going to head down from there, right? Does that make sense? So that is our net accumulation function, the one that we wrote, negative 0.75 times x minus 0.6. Does that graph make sense? If not, mull it over, ask one of us. So like I said, your homework for Wednesday, get GC on your computer, and then do the one-page review of today's lecture so that you're ready for Wednesday's lecture.